Section 14.4, Rate Laws. So a rate law shows the relationship between the reaction rate and the concentrations of the reactants. So if you were to have a reaction where ammonium and nitrite, so we have ammonium and nitrate, are reacting together, and you have a rate law where it's K to the ammonium to the first power and nitrite to the first power. What that means is if you double the concentration of ammonium, okay, so let's say you have twice as much ammonium at the beginning, it's going to happen twice as fast. If you increase, the reaction will happen twice as fast if you double the amount of ammonium at the beginning. Because since this is concentration to the first power, if I double this, okay, as this goes up, this will go up, okay? Also, this is to the first power, nitrite to the first power, which means if I double this, this will go up. So if I increase the concentration of one, the rate goes up. If I increase the concentration of the other one, the rate goes up. So the reaction is first order, meaning that it's to the first power in ammonium. It's also first order in nitrite. So if this is first order, if it's first order in ammonium and first order in nitrite, we're going to do a overall rate law of adding the two. Okay, so this is first order in the first order in the second, and there's two reactants in the everything on the left side of the reaction. That means overall it's going to be second order. It's based upon the concentration of the first, it's based on the concentration of the second. Those concentrations are to the first power. You add them together, and it's going to be a second order overall in this example. Okay, I'm going to wave a magic wand because in order to get this next equation, which is extremely useful, I have to do some calculus. The math itself is easy, very easy. When you get to calculus, you're going to realize that this is nothing. Adding was harder than this, but it looks scary and you don't know what you're doing, so you just accept it, all right? What you're going to do, what you realize is the natural log. You know what the logarithm, the log logarithm is. We're going to see the logarithm base 10 for when we get to acids and bases. We're going to use that on the calculator. You also have a button on your calculator called an ln button, and that's the natural log. It's not in base 10, it's in a different base. Don't worry about that. But you are going to relate two different concentrations. You are comparing essentially the concentration at any time, no matter what time that you pick, to the initial concentration. How much of that original concentration is left at any one time? Okay, so by doing this, by having two different things, you can answer all kinds of questions. You could ask yourself, how long is it going to take for this reaction to happen? Because up to now, you had no idea. You pour two things in a test tube. It could take a split second, or it could take thousands of years. Who knows? But if you had some idea based upon experimentation, you could make a guess within seconds of knowing exactly how long that a reaction is going to occur. And if you're making money on this, you want to know how long it's going to take. Is it going to take a day? Is it going to take an hour? Is it going to take a month? That depends upon how much money you can make, and it's interesting, not just interesting academically, but you want to know so that you can know what to do with your factory. So in any case, the natural log, which is just a button, over the concentration at any time that you pick, divided by the initial concentration that you started with, is going to be equal to negative, then there's the rate constant, times the time that you picked. Okay, so you can find out how fast it's going to go by the rate constant, and then know what the concentrations at any time. So you could say, after 6 seconds, how much product am I going to have made? Or after 6 seconds, how much of the original product original reactant do I have left? So there's so many questions that you could answer with this. So don't worry about deriving it, just use it. The natural log of the concentration of whatever you're talking about at any time divided by its initial concentration equals the rate constant times time. Now this, you have to know something about logarithms, and that's Algebra 2. So if you've had Algebra 2, it makes sense. If you haven't had Algebra 2, it looks like some kind of a strange foreign language. But essentially, let me tell you something that's true of logarithms. If you take the logarithm of a fraction, you're going to take the logarithm of the numerator, subtract the logarithm of the denominator. That's all it is. So what I'm saying is the natural log of this concentration minus the natural log of this concentration. That's just these two things are saying the same thing. All I'm doing is doing a math operation that you may not have seen yet, but that's all it is. It's simple. So that means that the natural log, if I subtract then, if I take this to the other side, the natural log at any time is going to equal negative the rate constant times whatever time I'm talking about plus the natural log of the initial concentration. Suddenly you've got something that you do know because this is a formula that you can graph. You can have something equals something times x plus something. So y equals mx plus b, if you remember, is a graph that is answered in a straight line. It's a straight line. Now remember, this is a first order reaction. So in order to get this, we took a first order reaction and integrated it, a little bit of calculus, integrated it. But what that means is a first order reaction will always graph as a straight line. Now that's useful. That's something that you can do right now. You'll know if something is first order based upon its graph. If it's a a straight line graph, then it must be a first order reaction overall. So not only is it going to be a straight line graph, but the slope of that line, the steepness of that line, remember the rise over the run of that line is going to be equal to negative k. Okay, negative k will be its slope, and the negative k is the constant that makes this math work, which is very easy to get. And in our practice, see, it looks terrifying now, but in our practice, this is going to be nothing. You can get this. You'll see it, and you'll see it as you play with it, you'll be able to understand it. That's all it is. All of this scariness goes away as you play with this stuff. That's why we practice every day. Okay, so we're going to take an example. We're going to take this guy and shift it around. So basically, the nitrogen is going to move from this side to this side. Okay, all we're going to do is kind of rework it. Since this is a gas, okay, and this is going to rework itself in a gas phase, we're going to use the pressure of the gas as its concentration. It works the same as a concentration. And we're going to see that over time, the concentration is going to drop, or the pressure is going to drop. And it's not going to drop in a straight line. It's going to drop in a curve. Okay, so we'll put that in our mind. So we're going to see that as the pressure drops in a curve, the natural log of that concentration or the natural log of that pressure plotted over time is going to go down as a straight line. That's going to tell me that that's a first order process. And remember, a first order process means that it's going to go to the first power. It's going to be something concentration to the first power. So therefore, the process is first order. Since it's a straight line, when I graph the natural log of it over time, it's a first order. And the negative k must be the slope. And if I can find the slope, all I have to do is take rise over run. Suddenly now I know k. That's really useful. If I know the rate order, if I know the rate constant, then I can find out how fast it's moving. How fast is it going to change? Because remember, it's the number that makes this math work. So it's not hard. It's easy. It's algebra 1 easy. But The concept, like why am I doing it, still may elude you, but the actual how to do it is going to be quite simple. Okay, so let's back up. If we have a second order process, remember a second order is going to be k to the a to the squared, okay? Something to the squared, which means if I double the concentration, the rate is going to go up by 4 times. So let's say I double it to 2a, okay, I double the concentration. 2a to the second is going to be 4a. That means as I double the concentration, the rate is going to go up by 4 times. So a second order process is going to be something to the second power, something squared. And if you remember graphing that, I don't know if you did it in Algebra 1 or you wait till Algebra 2, this is going to be a J-curve. This is going to be a parabola. When you graph an x squared, it's going to be parabolic. When you take the integration of this, okay, when you take the integration of this, you're going to get, instead of the concentration of a sub t over a sub 0 equals negative k sub t, you're going to get 1 over the concentration of a sub t equals k sub t plus 1 over 0. And we're going to see that this is also in this form. Y equals mx, and m is going to be k in this case. It's going to be positive k plus b. So what you're going to see is if you graph it, you are going to, if you graph 1 over the concentration of a sub t, okay, then you're going to end up with also a straight line. We'll look at this in a second. So we saw that if it was first order, okay, then graphing the natural log of the concentration over time is going to give you a straight line, okay, if it's first order. If it's second order, meaning that it's going to actually go to the x squared, then graphing 1 over the concentration, okay, 1 over the concentration per time is also going to give you a straight line. So these are 2 very useful ones that you could try. Simply graph one. If it's straight line, I mean, most of you have a fancy calculator. If it's a straight line, you know it must be first order. If you graph 1 over the concentration, so natural log of the concentration over time, if it's straight line, it's first order. If you graph 1 over the concentration per time, then if it's a straight line, then you must know that it must be second order. So let's look at an example, okay? Here is something, decomposition of NO2 at whatever temperature described by an equation. So you've got an equation here, all right? Then you have a set of data. At a certain amount of time, you've got this concentration. At 50 seconds, you've got this concentration, etc. Okay, so you have a data set. Now, what did I say? If you plot the natural log of the concentration per time, and if it's a straight line, then it's a first order reaction. Okay, so let's find out what the natural log of these concentrations are. So all it is you put this 0.01 in the calculator, push the ln button, and that's the natural log of it. Okay, so let's look at this. So if I have now the natural log of this concentration, okay, so I have a natural logs, and I'm going to put time on the bottom and natural log on the side, and I graph it. Now I'm looking for a straight line. Well, I don't have it. Okay, if that's not a straight line, then it's not first order. So that means that the reaction, the concentration, did not go to the first power. Okay, it must have gone to something else. Now, it doesn't go very much more. I always guess if it's either 0 power, which we'll look at, which means it doesn't change based on concentration, or it's not first power, it's more likely second. Okay, it's usually 0, first, or second, almost all the time. So if I graph the log of the concentration over time and get some kind of a curve, it's not first order. So my guess is either it's going to be 0 order or second order, and I would guess second order first. Okay, we'll look at that. So what was my second one? Okay, so if I graphed the natural log of the concentration over time and get a straight line, that's first order. How did I get second order? I graphed 1 over the concentration per unit of time. Okay, so Here was my concentration. So put that over 1. So 1 over that concentration, and here I've got this. If I graph the time to that and get a straight line, then I must have a second order process. So that means in the original, my concentration is going to go to the squared. That's what it is. So I need to know what these are in order to find my K. And we also see that the K is going to be the slope of that line, which is easy. I can simply just make a right triangle here and find out what the slope is. The last section or the last part of this section is called half-life. And we're going to see half-life in a couple places. We're going to see it here, and we're going to see it in chapter 21 when we get to nuclear energy and nuclear power. So when something decays, it's going to decay in a first-order process. If it's a first-order process, you're going to see that there is a certain amount of time that it takes to get to half of its amount. So remember, a first-order process is going to be linear. So there's going to be a certain rate the rate is constant. That means that since the rate is constant, it's breaking down. Let's say that something is breaking down like decaying. It's breaking down at a constant rate. Well, if it's breaking down at a constant rate, we can have an idea called half-life, which gives you the concept that after a certain amount of time, 1/2 of the amount of the original is left. So let's say that I've got a pound of uranium, and after a certain amount of time, I've got 1/2 pound of uranium. Okay? Well, the amount of time is based upon how much it takes to break down 1/2 of it. So let's say I have a pound, and after a certain amount of time, I have 1/2 pound, right? Because it's broken apart. Well, in that same amount of time, I'm not going to go down to 0. I'm going to now have half of my half. So the same amount of time it took to go from 10 to 5, the next half-life is going to go from 5 to half of 5, which is 2.5, and it's going to break down. And then the same amount of time, each time, you're going to have half of the remaining amount. So you're going to end up with, a certain amount of time. So the time is going to be constant. This time is constant. This time is constant. So in a certain amount of time, I'm going to have half what I started with. And then in the same amount of time, I'm going to have half of that amount. So this is half of this. This is half of this. And then so you're always going to have, in a first order thing, the concentration itself. Now, not the natural log of the concentration. The natural log of the concentration is going to go down in a nice, easy way, either building up or going down in a straight line. But the concentration, or in this case, the pressure, divided by time, is always going to be in a curve. And so that means that the same amount of time goes by, you're going to use up half. In the same amount of time, you're going to use up half of the half. In the same amount of time, you're going to have half of the half of the half. And these are called half-lives. And so the half-life, or the concentration of A at a certain time, is going to be 1/2 of the original. So if the time that we pick is going to be 1/2, then we can find out what the half-life is. And it's useful in anything that breaks down at a constant rate, like something radioactive. So the natural log of half of the original value divided by the original value is negative k t to the 1/2. T to the 1/2 is the amount of time it takes to break down half of the stuff. That's called the half-life. So we just kind of forced it here. The time is 1/2 of the amount, and so we went from half of it. How much time does it take to go from 1/2 of it? I just kind of forced it, and we realized that it's going to be whatever the constant is divided into 0.693. 0.693 divided by the rate constant is going to be the time it takes half of the material to decay. And that's useful in any kind of rate law situation, but very useful when we get to radioactivity. For a second order process, it's exactly the same. We simply just took the integrated rate law, and instead of the concentration of the at A sub t, we just took 1/2 of the original concentration, and it equals K sub t, but in this case it's K sub t to the 1/2. And then we solve for K to the 1/2, and we find for a second order process, the half-life equals 1 over the K, the rate constant, times the initial concentration. I just promise that as you use it, it makes sense.